Hello students, let's go to section 2, Applied Optimization. Here we're going to deal with a bunch of word problems, and here's the first example. It's a business example. Let y be the price of a certain product and let s of y be the number of sales. If you multiply them together, you're going to get the revenue. For instance, if the price tag is $100 and you sell 5 million of those, what's the revenue? Multiply, that's going to be $500 million. Now, the sales will not stay the same. It depends upon the price, and according to this model, if price is 0, then this part drops out and you have 8,000. That is, you can sell 8,000 with $0, which means it's not selling, you're giving away. Now, if you actually begin to sell with some positive price tag, then you're going to get this model basically. Now, if y is too big, then this will fall to negative, and that means not negative sale. Actually, it is simply saying that we are going out of the domain of this modeling. Now, this is typically the case. The price goes up, then the sales goes down. You see, you have all those negatives there. That's usually the case. In some cases, the sales may go up even as price goes up, especially under inflation, under the assumption, under the anticipation that price may go up even further later on. People buy anyway, and consequently driving the price even higher. Those kind of things can happen. But of course, those are all exceptional cases, and of course, this is not economics class, this is a math course, so let's just stick to what's given here. So that's my sales function. And then what is my revenue function? Multiply by y, so we get negative y cubed minus 40y squared plus 8,000y. That's it, isn't it? And then if you take the derivative and set it equal to 0, negative 3y squared minus 80y plus 8,000 equals to 0. So we are looking for horizontal tangents, so we have to take the derivative, set it equal to 0, and we ended up with a quadratic equation. You can solve it. Typically, you're going to have to use quadratic formula. In this particular case, which I got it from the textbook, we have such nice integers here, so factorization may be possible. But in reality, you'll never see those kind of examples. You're going to see all those numbers given by actual measurement. So you're going to have a lot of decimals flying around. If you have decimals, then you cannot do factorization. Those factorizations, those are all for integer coefficients only. So you have to put quadratic formula in there, like this. And then minus square root part, that's invalid because that's going to give you the negative value, negative price tag. So take only the positive square root and run your computation. In this particular case, you got $40 precisely, and that's because this entire problem here is highly unrealistic. Just a classroom example problem. I would not have written a problem like this. I would have given you some decimals flying around here and there, so that this computation gives you something like 41.26, something like that. Anyway, according to this, you get $40, so plug it in, and then you can get sales under that $40 price tag, and the revenue under that $40 price tag. This is the maximum revenue. Oh, by the way, here's a graph. Right here at 40, we have horizontal tangent. That's the maximum. By the way, I should have plotted beforehand. Yes, at this moment, right after getting the revenue function, I should have plotted. Okay, let's go to the next example. Sorry about that. Wrong cell. Okay, let x be the number of units sold and C of x be the total cost. Then the average cost per unit is as follows. Now this is not the average cost, but average cost per unit. Per unit, so that's why you're dividing by the number of units. Let's suppose that cost is modeled like this. So we have fixed cost of about $100 or $100 million, whatever unit. And then as we produce more, we have higher cost because all these have positive coefficient. So cost will go further up. And of course, we want to find out average cost per unit. So you'll have to divide by X. Find the number of units of the commodity that minimizes the average cost. So not this one, but you have to look at this thing. So we're looking at this quantity. Divided by X, so we get that. Divide by X, so we lose that. And then divide by X, like this. That's my average cost function. Oh, by the way, let me use power form. Yeah, that's more convenient. Instead of dividing by X, let's use X to the negative first power so that the derivative computation is a bit easier. Okay, let's go ahead and do that. And then what's the derivative? So what's the derivative? 1/4, and then this plus 4 just goes away, and then that's negative, and then we get negative second power. Is that right? And set it equal to 0. Check the derivative. Derivative of this is 1/4. Derivative of this, that's 0. Derivative of this, now negative comes out as coefficient, and subtracting 1 from the power, you get negative second power. Setting that equal to 0, you're going to get the X value that will optimize this C bar. And is it minimum or is it maximum? It's kind of difficult to tell. So why don't I plot it? X is going from, say, 0 to, well, X is going to negative first power here. It's going to denominator. So when I plug in X equal to 0, this will go to infinity. So it may not look very good, but let's plot it anyway. Let's see. Not bad, not bad at all. Like this. Interesting. Okay, all right, that makes sense now. So around here, we hit the minimum and bounce back up. Around X equals 20 or so, I'm not so sure. Just by looking at the graph, it's a little bit difficult to tell. Okay, let's find it out. Take the derivative, set it equal to 0. Looks like we have to solve this equation. And let's see, that is 100 over x squared is 1/4, isn't it? If I flip it over. So x squared over 100 is 4. If I flip both left hand side and right hand side, x squared is 400. X is plus or minus 20. But of course, minus 20 does not make any sense, so it should be positive 20. Okay, yes. As you saw before from the plot, we anticipated about 20. Yes, indeed, 20. Here's the solution. All right. Same computation as before. And, what did I do here? X squared over 100 is 4. I think I made a stupid algebra mistake here. What I did previously is correct. Flip both sides. X squared over 100 is approximately equal to 4. I have to flip both of them, you see. I have to do the left hand side and right hand side, the same thing to both sides. not just one of them. So x squared is approximately equal to 400. So x is approximately equal to 20. Negative 22, but that's negative value, so it's invalid. And then let's plot it. Plot this graph. Yes, we have minimum right here at x equals to 20. Yeah, right here at x equals to 20. Sorry about the previous error, but by the time you get this notebook, you will get corrected version, so don't worry about it. Okay. By the way, there's another problem here. Find the number of units that minimizes the total cost. Okay. Not just average cost, but total cost. That is, take the derivative of this guy and set it equal to 0. Okay, all right. Take the derivative and set it equal to 0. What do you have? Take the derivative and set it equal to 0. So that's 2x plus 4 is equal to 0. X is negative 2, which means that never happens. So close as possible there, x equal to 0. So that is the minimal cost. So if you produce nothing, then if you sell nothing, then the cost is nothing. Or you just have fixed cost of 100, no more. Oh, come on, that's a bit too stupid. Yeah, that's why I de-emphasize in gray. Mathematically, okay, it does make some sense, but in terms of business, doesn't make any sense at all. Just too stupid. How about the next problem here? C of x and R of x be the models of the total cost function and the total revenue function, so that subtracting one from the other, we get the profit function. Okay, the firm can produce up to 100 units of a certain product. The total cost function and total revenue function of the product are modeled like these. And find the number of units that maximizes the profit and find the maximal profit. Okay, all you have to do is subtracting one from the other, right? Revenue, so minus, and then cost. That's it, isn't it? And subtracting one from the other, I get negative x squared. And then, let's see, 1600 minus 1500, so plus 100x. And then minus 500. Okay, take the derivative, set it equal to 0, and you'll be able to find out the horizontal tangent. Looks like that's it. Actually, I forgot the plot. Yeah, like this. That's the maximum profit. If you sell too less, then you are negative, you are at loss. And if you sell too much, then cost is too big. So again, you are negative. At x equals to 50, that's when you can maximize your profit. Let's see. What do I have here in the answer key? Yes, the same computation. Oh yeah, by the way, P of 50, that's the maximal profit. Plug in x equals to 50 and do your computation, and 2000. That's going to be the maximal profit. All right, we went through some applied optimization, and then they all happen to be business examples, but of course I could have figured out other kind of problems too. Given function, take the derivative, set it equal to 0, that's basically it.